We started this semester by looking at the electric force between two charges, and then used what we knew about the electric force to think about this more abstract thing that was describing space. That was the electric field. What we saw was that the force depended on two charges. It depended on an interaction, and we could choose to label that interaction as between charge 1 and charge 2, or we could also choose to label that force as depending on the interaction between a source charge and a test charge. What made that framing useful was the fact that the field only depended on the source charge. So whatever your source charge was created the electric field, and then there was an electric force that was exerted on your test charge when you moved it into the electric field. We're going to do something very similar in thinking about the relationship between electric potential energy and electric potential. So we can define a new quantity called the electric potential and think about how it changes by thinking about the electric potential energy and its change, dividing out how that depends on the test charge. So again, we've seen the electric potential energy depends on both a source charge and a test charge. When we were calculating the electric potential energy, we called them Q1 and Q2. Here, we're going to emphasize that one of those is the source charge that's going to create the field. The second one is a test charge that we're moving around within the field created by the source charge. We're moving that test charge around in the electric field created by our source charge. And whether I move with or against the electric force lets me know whether I'm increasing or decreasing the electric potential energy. The electric potential and how it's changing, which is also called the potential difference, only depends on the source charge. So the source charge creates an electric field, and what the potential difference cares about is whether or not you are moving with or against that electric field as you move around from one point in space to another. It's easy to say. We're going to take the rest of this video to talk about what that really means. So let's take care of a couple of bookkeeping things before we get there. Units. Well, you can see from our equation here that the potential, electric potential, is going to have units of potential energy divided by charge. And so this is, energy has units of joules, charge has units of coulombs. So one way to write the units for electric potential is joules per coulomb. Of course, that comes up often enough, we've given it its own special name. That happens to be volts. One of the things that we'll need to be clear about is you might see a capital V. Do we mean the unit volts, or do we mean the quantity electric potential? We will use V for both of those. The other thing to just talk about right up front, it is tragic that these two quantities have names that are so similar, right? But they are distinctly different, right? One way to say they're different is they don't even have the same units. You can call the electric potential, you can talk about the change in the electric potential, you can talk about the electric potential difference. Because of its units, you will also see it referred to as the voltage or the voltage difference. All of those are the same thing. They're talking about this new quantity, the electric potential. As soon as you add energy on the end of that, you're talking about something different. So just one of the big battles we're going to have to fight here is just making it clear in your head, are we talking about electric potential or electric potential energy? Make sure right up front you're aware those two things are fundamentally different. They're related, but they're different. So to set up what we mean when we talk about the change in the electric potential, again, let's start by thinking about what we mean when we talk about the change in the electric potential energy. Well, what we said was the change in the electric potential energy of some charge as it moves in the presence of other charges indicates whether that charge is moving with or against the electric force that's acting on it. So as an example, if I've got two charges and they're both positively charged, I know that there's going to be an electric force that is repelling both of those charges away from the other one. So if I force them to move closer together, the electric potential energy will increase because I have moved those charges against the electric force that's acting on them. On the other hand, if I let those charges move away from each other, the electric potential energy will decrease because they're moving with the electric force. So it's easy to see when I have 2 point charges sitting near each other. But what happens when I have some really complicated charge on some complicated surface that's creating a complicated electric field? So I can take my test charge and put it into that complicated electric field. I can then move it around. And what I've done in terms of the electric potential energy of that test charge depends on whether or not it was mostly moving with or against the electric force that acted on it. Which means what I need to know is, was my test charge positive or negative, so I can think about the force that acted on it as it moved around. And so as my charge started somewhere over here, and if it moved somewhere over there, well, roughly speaking, in this area, right, even when it was coming backwards, right, the electric field is pointing away from my positively charged source here, which means that the electric force acting on this positive test charge would have also pointed away from the source charge. They're both positively charged. They're trying to repel each other, which means that the electric force is going to point away. And since on average, in moving from here to there, the test charge moved away from the field, it would have decreased its potential energy. If my test charge was negative, then the opposite would be true. A negative test charge would be attracted to my positive source charge, but I forced it to move farther away in general. So in going from this initial point to this final point, it clearly moved away regardless of what it did in between. So in going from my starting state to my final state, the electric potential energy would have increased on my negative test charge. So the electric potential energy cares about whether that test charge is positive or negative. What's interesting to see is that if I think about this equation sitting up top, well, we just said that in our example down here, delta U, the change in the potential energy, that would be negative if Q was positive. A negative quantity divided by something positive, that would give me something negative. On the other hand, if my test charge was negative, well, now the Q is negative, but of course delta U is positive. Positive divided by something negative still gives me something negative. So the interesting thing here is that what the electric potential is going to do is it's going to say the potential energy cares about the test charge, but I don't. I'm going to get rid of thinking about what's the charge that you're moving around in space. So the change in the electric potential as you move between 2 points in space in the presence of some charge indicates whether you are moving with or against the electric field. So a couple really important things to emphasize there. The biggest one is I'm not moving anything. So by dividing out the importance of the test charge, by removing the test charge, I'm not starting with some charge here and moving it there. I'm simply talking about this point in space and that point in space. So that's why the electric potential energy is describing what's going on as you move between 2 points in space. And again, all this cares about is whether or not you're moving with or against the electric field that depended on your source charge. And so what we see is the electric potential decreases if we're moving with the electric field as we move from point 1 to point 2. So again, in general, we're moving more with the electric field and going from point 1 to point 2 than we are against it. On the other hand, the electric potential increases as we move against the electric field in moving from P2 back to P1. So how I'm moving with or against the electric field in general indicates whether or not the electric potential will be increasing or decreasing. Because in general I'm moving with the electric field going from P1 to P2, the electric potential decreases. Because in general I'm moving more against the electric field in going from P2 to P1, the electric potential increases. The detail to notice, of course, is it doesn't matter what path I take to get there. So I could have taken this path straight from P1 to P2, or I could have taken an alternate path. Could have gone down first and then cut over. How you choose to move from one point to another doesn't matter. So the change in the electric potential doesn't care about which path you take. It only cares about whether in general you've moved more with or against the electric field. So to summarize all this, in general, if you move with the electric field and moving from point A to point B, so again from one point in space to another, the electric potential energy decreases. In general, if you move against the electric field and moving from point A to point B, the electric potential increases. If you move perpendicular to the electric field in moving from point A to point B, the electric potential remains the same. So the electric potential doesn't change when you move perpendicular to the electric field. So the detail that we're going to need to keep track of here is which way are we going? Are we going from A to B, or are we going from B to A? Because obviously the sign of the change in potential in going from A to B will be opposite the sign of the change in potential in going from B to A. So now that we have a better sense of what the electric potential is, let's come back and be clear about how, again, it relates to the electric potential energy. So here's a situation where I have a source charge that's sitting over here, and if I think about what's going on at this point out in space that I've labeled P, let's say that I know that the electric field points towards that source charge. Well, the first thing that does, of course, is it tells me that that source charge has to be negative. Right? We know that the field vectors point towards negative source charges, away from positive source charges. Here the electric field's pointing towards the source charge, which tells me that my source charge has to be negative. What would happen to a test charge if I released it from point P? One way that we can frame this is that regardless of what the test charge is, it's going to move to decrease its potential energy. So if you have a charge in an electric field and let it go, it will move to decrease its potential energy. So if given the chance, that's what it's going to choose to do. So let me rewrite the equation that we had before, where now I've got the change in the potential energy is equal to QT is the test charge that I'm moving around in the electric field. So this is the test charge whose potential energy I'm changing, multiplied by the change in the potential, the electric potential, between the 2 points in space that that test charge is moving between. If that test charge is positive, well, if it's moving to decrease its potential energy, left-hand side's got to be negative, which means the product over here on the right also has to be negative. If it's a positive charge, that tells me that my change in the electric potential has to be negative. What does that mean? Well, it means that when you release a positive test charge, it will move to points of lower electric potential. So, relatively speaking, point P out here in space had a higher electric potential than where my test charge ended up. This tells us that positive charges move from high potential to low potential. So if given the chance, they will decrease their potential energy by running downhill. And again, we'll sort of use gravity phrases to help us think about things in electric situations. And so downhill tells you that you're thinking about what the potential is and going from high potential to low potential. That's what defines downhill here. That was true for a positive test charge. What if our test charge is negative? Well, again, I know if I let it go, it's still going to move to decrease its electric potential energy. Q is now negative, which means my delta V term has to be positive. So again, that tells me that when I release a negative test charge, it's going to move to points of higher electric potential. So if P was higher than where my positive charge ended up, where my negative charge ended up is going to have an even higher potential than what it was at point P. This means that negative charges move from low potential to high potential. They decrease their potential energy by running uphill. One of the things that makes electricity different is that in having both positively and negatively charged things, I can talk about things that will naturally be inclined to run uphill versus downhill, as opposed to gravitationally, always positive mass, things always roll downhill. So this is why whether or not something's going towards a higher potential or towards a lower potential when I let it go depends on whether it's positively or negatively charged.